Have you ever looked at a really complex molecule, maybe some new drug or a high-tech material, and just wondered, how on earth did they build that?
Oh, absolutely. Or maybe you've been working through standard organic reactions and just, well, hit a dead end.
Yeah, like your usual chemical tools just aren't up to the job.
It's a very common feeling. For a long time, certain molecular structures seemed, well, effectively impossible for chemists to synthesize. Our traditional methods are powerful, sure, but they have limits, especially for making tricky carbon bonds or, say, sticking nitrogen onto an aromatic ring that doesn't want it. Some doors just felt locked.
Exactly. And that is the amazing story we're diving into today. Welcome to the deep dive. We're exploring organometallic chemistry, using Chapter 40 of Clayden, Greaves, and Warren's Organic Chemistry as our guide.
Right. And our goal here is to show you how adding transition metals to the organic chemist toolbox fundamentally changes everything.
It really extends the possibilities, letting chemists build these incredibly intricate molecules, and often with amazing efficiency and control. We'll dig into the why, the mechanisms, the reaction pathways, the new functional groups you can make, the stereochemistry.
And even how it changes the way you think backwards, retrosynthetically. This area is huge. Multiple Nobel Prizes. Huge. It's completely reshaped modern synthesis.
So just to give everyone a taste right away, what's a classic example?
Okay, think about the Heck reaction.
Yeah.
You take an alkene, maybe one that's not very reactive usually, and you precisely attach another organic piece to it. You form a new carbon-carbon bond, just like that.
And the magic ingredient.
A tiny catalytic amount of a metal, like palladium. It's not just a reaction. It's like architectural engineering at the molecular level.
Yeah.
Building things that were really hard, maybe impossible before.
Okay, let's unpack that. Metals.
Yeah.
We normally think in organic chemistry, right? How do they suddenly become these star players in organic synthesis? What's their secret?
Well, it all comes down to their electrons, specifically those orbitals they have. Unlike carbon or oxygen, these transition metals can juggle electrons in more complex ways. They can accept electrons, hold on to multiple molecules at once, bring them together.
Like a sort of molecular matchmaker.
Exactly. A chaperone, bringing reactive groups together in just the right way. And this lets them pull off transformations that just seem, well, apparently impossible using only traditional organic reagents.
Okay, but if they're catalysts, they need to be stable enough to handle, but reactive enough to actually do something? That sounds tricky. How do chemists manage that balance?
That is the key challenge. And one really useful guide, though not a perfect rule, is the 18-electron rule.
Ah, yes, the magic number 18.
Sort of. The idea is that a transition metal complex often achieves extra stability when the metal, counting its own valence electrons, plus those donated by the ligands attached to it, reaches 18. That's like achieving a stable noble gas configuration in its valence shell.
So it helps predict stability.
It's a great starting point, yeah. It helps chemists design catalysts they can actually store and use, but which are still primed for reactivity. You see lots of stable complexes like metal carbonyls or things like ferrocene following this guideline.
But you said it's not a perfect rule. Are there important exceptions we should know about?
Oh, definitely. It's a guideline, not dogma. You frequently encounter stable and highly important 16-electron complexes, particularly with metals like palladium, platinum, nickel, the later transition metals.
So things like the palladium catalysts we just mentioned?
Exactly. Many crucial PD-tie intermediates in catalytic cycles are 16-electron species. Their square planar geometry often lends them stability, even without hitting 18 electrons. And this ability to switch between, say, 16 and 18 electrons is actually fundamental to how many catalysts work. That flexibility is power.
Okay, that makes sense. Now, these ligands, the organic bits attached to the metal, is it always just a simple bond like a carbon attached to a metal?
Not at all. And that's where a lot of the richness comes in. Ligands can attach in various ways. We use something called the hapto number, the Greek letter N, to describe how many atoms of the ligand are directly bonded to the metal.
Okay.
So Pete1, eta1, means just one atom is bonded, like a simple alkyl group. But an alkene might bond through both carbons of the double bond, that's pp2. An allyl group could be Pete1, or it could bond through all three carbons in a delocalized way, which is Pete3. You could even have P5, like in ferrocene, or Pete8.
Wow, okay, so the way it attaches really matters for electron counting and stability.
Absolutely. Different bonding modes donate different numbers of electrons to the metal center. It's critical for understanding the 18-electron rule and predicting reactivity.
And the type of bond, is it just sigma bonds, or?
Good question. You get both. You have light complexes, where it's a straightforward sigma bond Think metal carbon, metal hydrogen, kind of like a Grignard, but with a transition metal. But then you also have chi complexes. This is where the metal interacts with the pi electrons of an unsaturated ligand, like an alkene or an alkene. The metal atom is kind of nestled into the pi cloud.
Okay, sigma and pi complexes. How does that interaction actually work electronically?
There are two key parts. First, the ligand donates electron density to the metal, usually from a lone pair or a filled sigma or pi orbital. That's donation. But then, crucially, the metal can donate electron density back to the ligand. This is called back bonding. Filled orbitals on the metal overlap with empty antibonding orbitals, usually p orbitals on the ligand.
Back bonding. What does that do to the ligand?
It significantly changes it. By putting electron density into antibonding orbitals, it weakens bonds within the ligand itself. Think of carbon monoxide bonded to a metal race. The CO bond actually gets longer and weaker because of back bonding. You can see this in IR spectroscopy. This activation is why metal-bound ligands become so much more reactive.
Okay, so unique electronics, the 18-electron guide, complex ligand bonding modes, sigma donation, pi back bonding. It's a whole new world of interactions. Now let's get into the specific moves these metals make, the elementary steps in catalysis.
Right. These are the fundamental transformations. Doesn't matter if it's palladium or ruthenium or iron. These basic steps form the vocabulary of organometallic reaction mechanisms.
First one, oxidative addition. Sounds like the metal is adding itself into another molecule.
That's a great way to think about it. The metal atom, often in a low oxidation state like M0, inserts itself into a single bond. Could be a carbon-halogen bond, even CH sometimes.
And oxidative because the metal's oxidation state goes up.
Exactly. It increases by 2 units, say from PD0 to PDA. And the number of ligands around the metal, the coordination number, usually goes up by 2 as well. Actually, the formation of a Grignard reagent is technically an oxidative addition of magnesium into the CX bond.
Huh, never thought of it that way. Are there different ways this happens?
Yeah, the mechanism can vary. Sometimes it's a concerted addition where both new bonds form at once, often resulting in cis products. Other times, like with methyl iodide adding to some square planar complexes, it looks more like an SN2 attack, giving trans products. Lots of mechanistic subtlety there.
Okay, if you can add, you must be able to subtract, right? What's the reverse?
That's reductive elimination. It's usually the payoff step, the one that forms your desired product and kicks it off the metal.
So 2 ligands on the metal joined together.
Precisely. 2 ligands combine to form a new single bond, maybe the CC bond you wanted to make, or a CH bond, and they leave the metal. The metal's oxidation state decreases by 2, going back down, say from M0, ready for another catalytic cycle.
Is there a key requirement for this to happen?
Yes, a really important one mechanistically. The 2 ligands that are going to eliminate must be positioned cis to each other on the metal center. If they're trans, they generally can't reach each other to form the new bond. It's a concerted process.
Okay, cis requirement. Got it. So oxidative addition breaks bonds and attaches things to the metal. Reductive elimination makes new bonds and releases them. How do you build up complexity on the metal before elimination?
That's often done by migratory insertion. This is how you can, say, insert carbon monoxide or an alkene into an existing metal-carbon bond, effectively growing the organic chain attached to the metal.
So one ligand migrates onto another?
Pretty much. One ligand, like an alkyl group, moves from the metal and inserts itself into an adjacent unsaturated ligand, like CO or an alkene, that's also coordinated to the metal. This also typically requires the 2 reacting ligands to be cis to each other. And crucially, if the migrating group is chiral, it usually retains its stereochemistry.
Can you give an example of where this is key?
Sure. In catalytic hydrogenation, using Wilkinson's catalyst, the hydrogen atoms are delivered to the alkene via steps involving oxidative addition of H2, and then migratory insertion of the alkene into a metal hydride bond. Or think about making ketones using iron carbonyls. You might have an alkyl group on the iron, then CO inserts into the FeZ bond, making it a sil group, then another step finishes the ketone. It's a sequence.
Right, building step by step. Now, what if you want to go the other way, like eliminate a hydrogen to form a double bond?
That's hydride elimination. It's essentially the reverse of adding a metal hydride across an alkene, which is a type of migratory insertion called hydrometallation.
Beta hydride, meaning a hydrogen on the second carbon away from the metal.
Exactly, the beta carbon. A hydrogen atom on that beta carbon gets transferred to the metal, forming a metal hydride bond, and simultaneously forming a double bond between the alpha and beta carbons, so the alkene leaves.
What does this need to happen?
It usually requires a vacant coordination site on the metal for the hydride to move to, and critically, The metal and the Vi hydrogen need to be able to get into a syn-paraplanar arrangement. They need to be aligned correctly.
Is this always desirable?
Often it's not. It can be a major decomposition pathway for metal-alkyl complexes you wanted to keep stable. If you want to do chemistry with a metal-alkyl, you often have to design the system to avoid foreign-hydride elimination, maybe by using alkyl groups that simply don't have any beta hydrogens.
Okay, so those are the core moves: oxidative addition, reductive elimination, migratory insertion, and bohydride elimination. The building blocks. Now, let's talk about the star player, palladium. Why is P so dominant?
Ah, palladium. It really is the workhorse, the most widely used metal in this kind of catalysis. Its power comes from, well, several things. One is incredible versatility. It works for so many different reaction types.
And it doesn't mess with other parts of the molecule.
Generally, no. It shows amazing functional group tolerance. You can have esters, ketones, amines, alcohols, all sorts of things elsewhere in your molecule, and the palladium catalyst often just ignores them and does its specific job. Plus, it usually has fantastic selectivity, chemo, regio, sometimes stereoselectivity.
But isn't it, expensive, precious metal and all that?
It is, but the key is that you only need catalytic amounts, sometimes parts per million levels. So economically, it's often very feasible. We usually use either palladium sources or palladium salts, which get reduced in situ down to the active PD0 species that starts the catalytic cycles.
Got it. And the Heck reaction is a cornerstone palladium reaction, right? One of the Nobels.
Absolutely. It's a fantastic example. Basically, the Heck reaction couples an organic halide or triflate, typically aryl or vinyl, with an alkene. You make a new substituted alkene and forge a new CC bond.
Walk us through the cycle again, using those steps we just learned.
Okay. Starts with active PD0. First step, oxidative addition of the organic halide to PD0, making an RPDX species.
Right. PD0 to PDE.
Then the alkene comes in and coordinates. Next is migratory insertion, specifically called carbopalidation. Here, where the R group migrates onto the alkane.
Extending the chain.
Yep. Now you have a new alkyl palladium species. This intermediate then undergoes hydride elimination. That forms the new double bond of your product alkene and leaves you with a HPDS species.
And the final step.
You need a base. The base reacts with HPDDX to eliminate HX and regenerate the PD0 catalyst. And the cycle begins again.
It seems remarkably flexible.
It is. It's very accommodating, as Clayden puts it. Works with lots of different alkenes, various bases. And you get good regioselectivity, especially if the alkene has electron withdrawing groups. The new carbon usually adds to the less hindered end, beta to the withdrawing group. It's used everywhere, making complex heterocycles, functionalized amino acids, just indispensable.
Okay, couples halides with alkenes. But the real power comes in coupling two different organic pieces together, right? The cross-coupling reactions, another Nobel area.
Yes, arguably even more impactful, these cross-couplings. This is where you take, say, an organic halide R2X and an organometallic reagent R1M, and you precisely stitch R1 and R2 together using a palladium catalyst.
So R1, R2, what's the general mechanism here?
It also starts with oxidative addition of R2X to PD0, giving R2 PDIIX. Then comes the really key step, transmetallation.
Transmetallation. Metal swapping?
Kind of. The R1 group from the other organometallic reagent, R1M, where M might be tin, boron, zinc, magnesium, silicon, transfers from its metal onto the palladium, kicking out the MX species. Now you have R1PDIR2.
Ah, both pieces are on the palladium now.
Exactly. And they need to be cis for the final step, reductive elimination. R1 and R2 couple together, forming your desired R1-R2 product and regenerating the PD0 catalyst.
Brilliant. Any constraints on the R groups?
Well, for the R2X partner, it's usually best if it doesn't have bowed hydrogens, because that oxidative addition product, R2PDX, can hang around for a bit while waiting for transmetallation, and you don't want bohydride elimination to happen as a side reaction. The R1M part is incredibly versatile, though. That M can be lots of different metals.
And this versatility gives rise to all those named reactions. Still, Suzuki.
Precisely. The still coupling uses organostanins, R1 SNB-Vu3 typically. Great for coupling various Seb2 and SPO carbons, even for making challenging macrocycles. You can even combine it with COH2.
And Suzuki. That one seems everywhere.
The Suzuki coupling uses organoboronic acids or esters, R1BOH2 or similar. It's incredibly popular, mild conditions, often air and water tolerant. The boron byproducts are generally less toxic than tin. It's fantastic for making birals, connecting aromatic rings together, which is huge in medicinal chemistry.
How does it work mechanistically? Anything special?
The key difference is the transmetallation step. It usually requires a base. The base activates the boronic acid, forming a more nucleophilic boronate 8 complex, which then transfers the R1 group to the palladium much more easily. It's also known for excellent stereoselectivity. When coupling vinyl boronic acids with vinyl halides, you can make dienes with precise, easy geometry. And it tolerates bulky groups really well.
And Sonogashira for alkynes.
Right, the Sonogashira reaction couples terminal alkynes, R1CCH, directly with aryl or vinyl halides, R2X. Usually uses palladium and a copper I co-catalyst under very mild conditions. It's crucial for making things like conjugated polymers and, interestingly, endynes molecules that can undergo Bergman cyclization, which is relevant to some anti-cancer drugs.
Okay, switching gears slightly, allylic systems. You said they're messy with normal reactions. How does palladium fix that?
Palladium works magic here by forming call-out complexes. When PD0 reacts with an allylic electrophile, like an allylic acetate or halide, it doesn't just do a simple oxidative addition to one carbon. It forms a complex where the palladium is associated with all 3 carbons of the allyl system carrying a positive charge, essentially a delocalized allylication complex.
And then a nucleophile attacks this complex.
Yes, and here's a really cool part about the stereochemistry. The palladium usually adds to the face of the double bond opposite the leaving group inversion. Then the nucleophile typically attacks the allyl complex from the face opposite the palladium, another inversion.
So double inversion, meaning overall.
Overall retention of configuration. It's a beautiful mechanism that allows for highly stereo-controlled allylic substitutions. You can take a chiral allylic acetate, react it with a nucleophile via palladium, and get a chiral product with the same relative stereochemistry. It's incredibly powerful.
Are there particularly good starting materials for this?
Vinyl epoxides and allylic carbonates are great because the leaving group, once it leaves, can actually act as the base needed later in the cycle, allowing the reactions to run under very mild, almost neutral conditions. This is fantastic for complex synthesis, like in Trost's work building intricate natural products.
Palladium can even mediate cycloadditions, like 3+2?
It can. There's a specific palladium-catalyzed 3+2 cycle addition using a special trimethylmethane, TMM, precursor. Palladium essentially stabilizes a TMM equivalent, which then reacts with electron-deficient alkanes to form 5-membered rings, like cyclopentanones. It's a stepwise process involving conjugate addition, then allylic alkylation, but the net result is a 3+2 cycload addition.
Incredible control. Now, what about those really tough bonds, carbon to heteroatom, like nitrogen or oxygen, on an aromatic ring, especially if the ring isn't activated?
Ah, yes. For decades, that was a major headache. If you didn't have strong electron-withdrawing groups to enable traditional SNR chemistry, you were often stuck. That's where the Buchwald-Hartwig amination comes in, another Nobel-recognized achievement developed in the 1990s.
So this lets you attach amines or alcohols directly to aryl or vinyl halides.
Exactly. It allows nucleophilic substitution of amines or alcohols thiols onto aryl or vinyl halides and triflates, even when the ring isn't electronically activated for SNR.
What's the mechanism? Still palladium.
Still palladium. Starts with oxidative addition of PD0 into the RX bond. Then the emming, or alcohol, coordinates to the palladium. A base is crucial here. It deprotonates the coordinated amine, making it a better nucleophile and helping to eliminate HX. Finally, reductive elimination occurs, forming the desired CN, or CO, bond, and regenerating PD0.
How general is it?
Extremely general. Works with aryl iodides, bromides, chlorides, which is great as they're cheap, and even triflates. And it works with a huge range of amines, primary, secondary, anilines, even ammonia equivalents. It's revolutionized the synthesis of pharmaceuticals and materials containing these linkages.
So how does it compare directly to, say, SNR? When would you choose one over the other?
It's about the electronics. SNR needs those electron-withdrawing groups, like nitro groups, ortho or para, to the leaving group, to stabilize the negative charge in the Meisenheimer intermediate. Buchwald-Hartwig doesn't. It works well on electron-rich, electron-neutral, and electron-poor rings. So if you have strong activation for SNR, that might be simpler. But for almost everything else, especially complex fragments in drug synthesis like assembling parts of itraconazole, Buchwald-Hartwig is the go-to method for making those ARN or ARO bonds reliably.
We've talked almost exclusively about PD0 cycles. What about palladium-2? Does it do different things?
Yes, PD itself can act as a catalyst, often by activating alkenes towards nucleophilic attack. When an alkene coordinates to the electron-deficient PDD center, it pulls electron density out of the alkene's pi system.
Making the alkene electrophilic.
Exactly. It activates the alkene for attack by nucleophiles, even relatively weak ones like water or alcohols.
Yeah.
This is like activating an anon for conjugate addition, but using PDD instead of a carbonyl group. Attack usually occurs at the more substituted carbon of the alkene.
But if the nucleophile attacks and PD tie gets involved, doesn't it often end up as PD0? How do you make that catalytic?
Good point. Often the PD2 is reduced to PD0 in the process. To make it catalytic in PD2, you need to add a reoxidant to the reaction. This oxidant takes the PD0 formed and converts it back to the active PD type. Common oxidants are things like copper to chloride, often using oxygen from the air as the ultimate oxidant, or benzoquinone.
And the classic example of this is?
The Wacker oxidation. This is a cornerstone PD tie catalyzed reaction. It converts a terminal alkene, a vinyl group, into a methyl ketone using water as a nucleophile and typically QCl2O2 as the reoxidant system. The mechanism involves coordination, nucleophilic attack by water, oxypalidation, and then phi hydride elimination steps.
So PD tie is great for oxidizing or activating alkenes.
Yes, or rearranging things. You can oxidize silyonyl ethers to anions or isomerize allylic acetates using PD-tyne catalysis too.
Palladium is clearly the superstar, but you mentioned other metals. Are there other key players we should be aware of?
Definitely. While palladium gets a lot of attention, other metals have carved out crucial niches. Gold, for example, has seen a huge resurgence.
Gold? Isn't that even more expensive?
Or gram, yes. But catalytically, it can be quite effective and sometimes even cheaper overall depending on the reaction. Gold catalysts, often OTIA or R, are fantastic at activating alkynes. They act as soft, Pacific Lewis acids.
Activating alkynes for?
For attack by nucleophiles. The hydration of alkynes to ketones or complex intermolecular cyclizations involving alcohols or other nucleophiles attacking the activated alkyne. Gold catalysis often proceeds under very mild conditions and can lead to unique skeletal rearrangements.
Okay, gold for alkynes. Anyone else?
Ruthenium is another major player, particularly for alkene metathesis.
Ah, olefin metathesis. Another Nobel Prize winner. That sounds completely different.
It is conceptually revolutionary. Metathesis reactions essentially allow you to cut carbon double bonds and recombine the fragments in new ways. Imagine taking two different alkenes and swapping partners to make two new alkenes. Or taking a molecule with two alkanins and joining them to make a ring. That's ring-closing metathesis, or RCM.
How is that even possible?
It requires specialized ruthenium catalysts, like the Grubbs catalysts or Hoveyda-Grubbs catalysts. These catalysts mediate a complex cycle involving metallocyclobutane intermediates. It's an incredibly powerful way to form CC bonds, especially for making rings of various sizes or for coupling complex fragments. It's used extensively in polymer chemistry and complex molecule synthesis, making drugs, natural products like malayamycin A. It's transformed synthetic strategy.
So when you put all these tools together, heck, Suzuki metathesis, maybe some gold chemistry.
The possibilities become immense. You can see this in ambitious total syntheses. For instance, the Hedgedis synthesis of N-acetyl clavucipidic acid methyl ester, which is highlighted in Clayden. It cleverly combines multiple palladium steps, a Hick reaction, a PDE by I mediated cyclization involving alkene activation within a single synthetic sequence.
And it works efficiently.
Remarkably so, achieving a good overall yield for such a complex target. It's a perfect illustration of how understanding and applying these organometallic reactions allows chemists to devise elegant and powerful retrosynthetic plans, building complexity step by step with high precision.
It really is an amazing expansion of the synthetic toolkit. We've gone from fundamental principles like the 18-electron rule and back bonding through the elementary steps and seen how palladium, gold, and ruthenium orchestrate these incredible transformations, building CC bonds, CM bonds, rings, complex architectures, often with fantastic control. It truly unlocks reactions that seemed impossible just a few decades ago.
Absolutely. And maybe this brings up a final thought for you, our listener. Consider how these seemingly small mechanistic details, the cis requirement for reductive elimination, the syn requirement for hydride elimination, the subtle dance of electrons in back bonding, the meaning of a hapto number, how these are the fundamental rules of the game. It's by understanding and mastering these rules that chemists can design strategies to build incredibly complex and vital molecules, like new medicines. So how does seeing this blend of inorganic principles and organic reactivity change your view on what's achievable in synthesis? It really pushes the boundaries, doesn't it?
It certainly does. A powerful perspective to end on. Thank you for being part of the Deep Dive family today. We hope this exploration of organometallic chemistry has given you a valuable shortcut to being well-informed and maybe spark some new ideas about molecular construction.